It's enjoyable. It's very fun. So it's a historical musical slash rock concert of Henry VIII's ex-wives. There were 6 of them.
I've heard of this.
That's why it's called 6. It goes through each of them. And, they're different genres of music, very interesting, but they're all so fun. I went and saw it while it was in Sydney with some friends, and oh my goodness, that show is deeply entertaining. And the music's on Spotify. I recommend giving it a listen.
I've heard some of the songs.
I'm not a big musical man, but I'll
Really?
maybe give it a listen. Yeah, I generally dislike musicals.
Would you prefer a musical about the number 6?
Potentially.
I feel like you would.
You feel like I would like musicals?
Yeah.
I give musical vibes?
I figure you'd like a musical about the number 6.
Oh, I see.
I feel like you could get really into, like, the intricacies of what 6 can do and, like, the factorization and the number theory of it all.
Set theory to determine, what 6 really is.
Successor function. It's like the 300-page proof that 1 + 1 = 2.
No, I don't like this.
Yeah. I feel like you guys are going to get too excited about this if I let you guys keep talking about it.
I feel like we should be doing this in the podcast. Like this discussion should be happening.
I have good news for you. Good after morning, and welcome to On the Dome, a podcast about how non-expert college-age youth think. And for our very last episode of the semester, very special episode, we're going to be talking about what we were just talking about, which is math. And I have some very special guests for that. So if you'd like to introduce yourself.
Yeah, I'm Ellery Stoller. I'm from Manchester, Vermont, and I'm in 18C, which is Math with Computer Science.
Very nice.
I'm Liam Coy. I'm from all over the place, but most recently Sydney, Australia, and I am a Course 22 major, which is Nuclear Science and Engineering, but I did a lot of math in high school. A lot. Maybe a little too much math, some might say.
I did some competition stuff in high school. I was never, in it enough to be, winning anything, but I just did it every year, and, math is so cool. Math is...
Yeah. Did you do the AMC?
I did do the AMC.
That's the classic one.
I never made it to the AME.
That's the classic one.
But one year I got really close.
Nice.
But I never made it.
It's difficult. It's hard.
It is difficult.
Did you make it to the AME?
I did make it to the AME. junior and senior year.
Very nice.
See, we
didn't make it past that. But
No.
We also had an AMC in Australia, but, it stood for Australian Math Competition instead.
Oh.
I did well most years, but there was, 1 year when I took it, and I just completely failed the entirety. Because, one, I was sick that day, and two, the AMC in Australia is an hour-and-a-half thing, right? And then there are these other math competitions, which are 4.5 hours for 5 questions, right? And the AMC is 30 questions in an hour and a half.
Okay.
And, my brain just was not working at all that day. So I'm just staring at this piece of paper, going, I don't know what's happening here, but I've got plenty of time. And then I look at the clock, and it's I do not have plenty of time. I only have 15 minutes left, and there's oh, no.
Yeah, AMC is very much a speed run, especially in the United States as well. I think it's, 25 problems, 75 minutes?
Yes.
Yeah.
So you have to, gun through the first 15.
Yeah.
And then just, hope on the last maybe 5, 10.
Yep. Now, I remember one of the years I actually did well. So 30 problems, right? And, it's an hour and a half, but that was basically 2 school periods at my school, right? So halfway through taking the exam, the bell would ring, and we'd all go, I'm trying to work here, but okay. So when the first bell rung, I had finished the first 29 problems. And I was feeling pretty good about myself.
Speedrun.
The entirety of the second period was looking at this one problem 30, and just going, why is no method I'm attempting here working? How do you do this problem? What is going on? Managed to get it with 5 minutes left, but,
wow.
That was...
Did you get all the first 29 right? Did you get a perfect score? There's no way.
I got a perfect score one year that it might have been that year.
Holy.
Good job.
Jeez, bro.
Yeah, no, my scores, they had some variation. Variance was high.
Wow.
I feel like math competitions, I feel like the AMC was good at getting me interested in math for the first half of the amount of time I was studying for it. So freshman and sophomore year, I did it and I prepped for it every year. And freshman and sophomore year, every year I would just be so excited about it. I'd be like, yes, this is so good. AMC 10, here we go. And every new thing I learned, I'd be more excited about it. And then junior and senior year, I'd prep for it and be like, oh God, geometry.
No. I was so bad at geometry. That was my worst
geometry.
part.
Yep, likewise.
Did you do any in middle school? Did you do math counts in middle school? Or?
I didn't do math counts.
Okay.
I did AMC 8, and then we did, it was I did something. It was not math counts. It might have been a local thing.
Okay, yeah.
It was something like that.
Nice.
So geometry was also oftentimes my least favorite thing.
Triangles. All my homies hate triangles.
Triangles in circles.
Oh my! I was just about to say that. I was just about to say that.
There are too many circles for any triangle. A triangle does not need to define that many circles.
Exactly. And there's so many random theorems, and so you
Yep.
know that there's that one kid who just knows everything.
Yep.
And is just answering them in 10 seconds, and then I'm here trying to rederive
Derive
it.
everything.
Yep. One of my friends, this was during one of these exams practice at the rather pretentiously named AMOC School of Excellence for math. One of our final problems on an exam was this geometry thing, and he had done a lot of work, but he just didn't know where to go because what he had reduced the problem to was proving that these 6 points were all on a circle, were all concyclic. And he was just I have no idea how to do this. And it turns out that there is a theorem that literally says if you have 6 points in this arrangement, they are concyclic. And he was just oh, that would have been nice to know. I spent half an hour working on it, but okay.
That's funny.
And for me, at least, the problem with geometry is that it was always either magic solution, just construct this line and everything works out.
Right.
Why would you construct it?
Who knows?
Or it was just this awful bash.
Angle chasing trig bash.
Yep, a trig
Yep.
bash, a complex bash, a
Yep.
coordinate
Yeah.
bash. Ugh.
Throwbacks.
I like my algebra. I like the stuff that I like reproving was we talked about this, the theorem with the it was if you add up the sum of numbers 1 through n, and then you add up the sum of those same numbers cubed.
Oh, yep.
Yes.
And it was a question where it was you have 1 plus numbers, number, all the way to 5,000. And then you have that, and then this has some property. Now, tell us that same property about that same thing cubed.
Oh, yeah.
And I
Some
was
modular arithmetic problem? Is that?
I think you might be able to do it with modular, but it was essentially what you either had to know that the sum of 1 through n versus the sum of 1 through n, 1 cubed through n cubed, the second one is the square of the first one.
Yes.
And so what I did was well, there must be some easy way to do this. So what I did was I was 1 plus 2 plus 3 plus 4. What's that?
Yep.
Okay, what's 1 cube plus 2 cube plus 3
Yep,
cube
yep,
plus 4
yep.
cube?
Try small cases.
The engineering proof, yeah. Just
No, legitimately, I possibly did a little too much math in high school. I will say this again and again. But one of the things that was drilled into my brain by pretty much every single good instructor I had was try small cases.
Yeah.
Right? Problem might make no sense, but hey, maybe you see a pattern. It's at least now I kind of know what I want to try and prove.
Yeah.
Right.
Even if I don't know how it's true in any sense.
I mean, a lot of algebra problems and stuff like that as well will have strictly relatively small solutions sometimes, and then you can prove if you get 3 solutions in a small range, you can prove that there's none that exist bigger than 10, or none that exist lower than -5, or something like that. And that's oftentimes a lot easier to prove.
Yeah.
And then you just check all the numbers in that range.
But you were more of a number theory guy, right?
I enjoyed number theory.
How about combinatorics?
I also like combinatorics.
Ooh, combinatorics are fun.
Yeah.
Counting stuff, but fancy.
Yeah, we have there's art of problem solving.
Oh, yep.
Oh,
Yeah, so
no.
I did a couple classes through art of problem solving. I did their number theory course, and I did counting and probability. Those are the 2 classes that I took over the summer.
I did a very similar course. So we had this thing called the Robinson Center, which is at the University of Washington. It's basically they put on different summer classes at the university I think that it's with maybe like students or professors at UW. I'm not sure. But I used to do that every summer. I would be at UW and it would be some different class. And one of them was number theory, and they used the AOPS book.
Oh, nice.
It was a good class and it was a bad class. It was a good class because the concepts and the stuff was really interesting. It's a bad class because some of the people were not exactly the most fun to be around.
What flavor of not fun? Just like
boring,
haven't practiced social interaction ever in their life, or needlessly cruel, or somewhere in between?
We had a variety mix.
Variety pack, the fun.
No, there were some interesting people. There were a lot of guys who really, really liked math and didn't necessarily have, had low opinions on people who did things other than math.
Oh, yeah. Yeah. No, especially if you're looking at advanced classes or Olympiad things or any sort of that sort of stuff, you will tend to get your fair share of people who just really, really liked being the best at things and kind of love making it known how good
their whole personality is just like, I'm really good at math.
Well, they were like, this was, I was in, 8th grade, and it was probably from 7th grade through, 10th grade.
Okay.
There was, of course, the one, 5th grader.
Always.
Always. Every time. So, I mean, I'm sure they've grown up to be wonderful people, but at that point in their lives, they were not extremely wonderful.
Yeah. It happens sometimes. But also, wait, so just going back to that probability course you mentioned, is that why you knew the boy born on a Tuesday problem?
Yes.
That makes sense. So,
have we told you the boy born on the Tuesday problem?
You've told me, but I want you to tell me again.
Do you want to explain it?
All right. So, someone comes up to you, in a park, on the street, something, and they're like, hey, I have 2 kids.
Okay.
You go, okay, a little weird, but thanks for telling me this, random stranger. Lovely. And then they're like, hey.
Do you want to start the easier case of...
All right. So, and then they're like, hey, I have a boy. Right? And for the sake of this problem, we're assuming that, boy, girl are the only options, and they're each equally likely, right? So a random child has a 50% chance of being a boy, 50% of being a good. Like, we aren't taking into account real-world stuff, because mathematicians don't do that.
Right.
No.
Assume a spherical cow.
Hey, that's physics.
That's physics.
Math is one step further. But yeah, so then the question is, given all the information that you know, that this person has 2 kids and that this person has a boy, what is the probability that their other child is a boy?
Okay. I'm not going to answer this because I've definitely already answered it, and I've definitely already answered it wrong. So we're just going to leave this. It's an exercise to the viewer.
Now, the answer is not 1/2.
Right.
And that's the instinctual answer, because you're just like, why does this information matter? The answer is actually 1/3. And the reason for that is, well, you want to go through it?
Yeah, so pretty much by knowing that one child is a boy, there's 4 possibilities for the children if you break it down into, child 1, child 2, right?
Right.
So either, child 1 is a boy, child 2 is a boy, girl, boy, girl, right?
Right.
So by knowing that 1 is a boy, you rule out the case of girl. Everything else is equally likely. Right. So the probability that both is a boy is, the boy over, your whole sample space, which is, boy, girl, boy. So it's 1/3 chance.
Yeah. Which is awesome, because probability is incredibly counterintuitive sometimes, which is great. Now, here's what makes it even more counterintuitive. But before we actually go into that other version of the problem, so, if the stranger had come up to you and said, hey, my older child is a boy, completely different scenario, because in this case, it is just 1/2, right? Because then the only 2 cases left are boy-girl or boy-boy, right? And they're both equally likely. Now, this time the stranger's even stranger than last time. The stranger comes up and is like, hey, I have 2 kids. Okay. You're same as last time. But then they say, hey, I have a kid who is a boy born on a Tuesday.
Right.
What's the probability that their other child is a kid this time?
I'm going to try and remember what the answer you gave. I will say I've answered this wrong, and I'm going to, if I try and think about it, answer it wrong again, which I'm fine with. But I think what the answer you gave me was something like 13/27.
13/27 is correct.
You got it.
Which is really weird. Why does this information matter?
No.
I mean, if you ask them, so if it was the first case again, and you're like, before I answer this question, I want more information. You said you had a child who was a boy. what day of the week was that child born on? And they told you Tuesday. Well, it's still a third as the answer. Right. The probability is still a third. But if they just like randomly volunteer this weird information, the probability changes to 13 over 27 out of all numbers.
Which is not necessarily that close to 1/3 either.
No, it's really close to a half.
It's really close to a half. And it's kind of like the more information you give, the closer to a half you get. So if they say, I have a boy who's born on Christmas, I forget what the actual probability ends up working out to.
364 over 730.
729, no?
720, no, 730. No, 729.
729.
729 is a...
it also happens.
729.
There's a reason for it being 729.
Not it being a power of 3, actually, funny enough. That's not.
But that's a reason that you can remember it.
Oh, that is a reason you can remember it.
Yeah. Pick the pretty number.
Yes.
The pretty number. Yes.
Yeah, so TLDR, probability is really counterintuitive, but really cool.
Yeah.
I want to mention that you did bring this up to me before, and I want to mention the situation, which is it was 1 a.m., and we were in the cafeteria eating and trying to de-stress from P-sets, and you were like, I know what's going to help this situation. But I've been told about you, and I've experienced about you, is that you bring up math at every opportunity and in every scenario. I've been told, I was talking about this yesterday with a friend of ours, and they were like, yeah, so Ellery was partying really late, having a really good time, and then he starts talking about math.
Fascinating.
Which time was this? Because there are plenty of times I can think of.
What?
Any time we talk about a random variable. The amount of times that we have just been, like, out somewhere, having a good time, and just, like, modeled. So, we're both taking this class, 18600, probability and random variables.
Right.
Fantastic class. Would absolutely recommend taking it.
We were just talking about this, like, before we left.
Yes.
Like, how we would model our leaving time.
Yes, we were. And this is a perfect example. So, what the class is about, random variables, are these things that we use to model randomness, basically.
Yeah, they're like variables, but they're functions.
Yeah, in a way.
They're kind of interesting.
Mm-hmm.
Yeah, so I guess a good example of one is if you were to flip 100 fair coins, right? And, figure out how many heads you would get. On average, it would be about 50, but there's this weird distribution of how many specific heads you get.
Right.
And that's a binomial random variable. And, you have 100 flips, and there's a probability for each flip of being heads. And there are a ton of other types of variables that are used in different contexts. And very, very, very frequently, we apply them to events in our lives.
Yes. Like grade distributions, what time we're going to leave for something. It goes on.
The number of chance meetings with people.
Yes, the number of parties of a century in a 1 month period of time.
Oh, wait, tell me more. Tell me more about this.
So, we were just like, there's like a 1 month stretch where there were just like 3 parties that happened, and we were just joking, like, this is the party of the century.
Right.
But, so if you have something that is like genuinely a party of a century, what's the probability that you would see 3 parties of a century in a 1 month period of time?
If one of them is a real party of the century.
So all of them
are genuine parties of the century.
Yeah. So if a party of the century is defined as a party so good that a party of that quality on average only occurs once every century.
Right. Same way you can have like an earthquake of the century, but like, you could have like them one day and like 1 day apart, but like
it would just be really sad.
Right.
So there's a random variable called a Poisson random variable that is explicitly used for modeling this sort of.
Spell that for me. Spell me that word.
Fish, but in French.
Is it poison with 2 S's?
Yep.
Yes.
I like that.
Yeah. Why is it called that?
I think there's a guy's name. I could be wrong. I don't think it has to do with fish.
I want it.
Yeah. I hope it has to do with it. Anyway, so this random variable in real life is used for things like modeling earthquakes, right? Because it models extremely rare events. Basically that's all you really need to know about. And it's got a bunch of weird math for how exactly it works out. But we decided that the probability of seeing 3 parties of the century in a 1 month span of time was what?
E to the minus 1 over 1200 times 1 over 1200 to the 3rd power over 6.
Yep, so...
3 factorial, yeah.
So a very small number, considering that we have a 1 over 1,200 cubed in the numerator
Right.
there.
And in... Actually, never mind. I was going to say e to the minus 1 over 20.
Yeah,
that doesn't... 1. Yeah, that's effectively 1, though.
But... for reference, the parties of the century that did occur, well, first there was DTYD, Dance Till You Drop, of course. That's a fantastic event.
Classic.
I actually forget what the second one was.
I also forget what the second
But
one was.
that's how you know it was good.
That's a concerning statement there, but maybe that one just wasn't a proper party of the century.
Yeah.
But then the third one was a Cinco de Mayo party, affectionately known as Sigmo de Cayo.
Very nice.
These were all certainly events, and they happened.
They did.
And that's about what I have to say on them.
Yeah.
And of those 3, how many did Ellery talk about math at? At how many did Ellery talk about math?
Well, you didn't actually attend DTYD.
I was not at DTYD. I had the video game orchestra concert that day, and I was very tired after.
Oh, but you did talk about math that night.
What?
Yes.
I did?
Yes.
Wait.
Before.
When? Did I?
Yes.
Very plausible.
I'd believe that.
Yeah.
I remember because I did go to DTYD, and we were hanging out before in Simmons, and we were talking about
Yeah,
that.
like a 95% confidence interval. No, I'm kidding.
That I know because I did take AP Stats, but
There you
that's
go.
about the probability.
There you go.
Look, if you liked anything at all that happened in AP Stats, take 18600 because
Yeah.
it's so much better.
Oh,
It
that's
just, like-
it's an interesting way that you phrase that. Me and my friend back home, we used to call the night before every AP Stats test and be like, okay, so you didn't do any of the stuff, right? And we were like, yeah, no, we didn't do any of the homework, didn't do any of the readings, slept through the classes, sorry, Kathy.
Very nice.
And then we would call the night before the test and just read the chapter and be like, okay. And then we would go and do the test.
See,
Nice.
in my AP statistics class in high school, class participation was very low. So I was the only one who participated, really, but also I would play Minecraft the whole class.
Oh.
And the teacher would see this, but she wouldn't really care, because I was the only one who participated, so she'd be like, Ellery, stop that. Wink. And I'd be like, okay, sounds good. And I'd continue to play Minecraft, and I would raise my hand and answer questions.
While playing Minecraft.
So out of curiosity, what happened to this wonderful participation that you exhibited in AP Stats? Because you did not participate in all in any of the classes we shared this semester.
Yeah.
Even when you explicitly knew the answer, like you discussed the answer with me, I was like, yes, this is the correct answer, you should say it.
Yeah, it's something to work on.
Honestly, I've actually kind of noticed that in a bunch of the classes here. People are all just so terrified of saying the wrong answer in front of everyone that it's just dead silent.
Yeah.
And I despise waiting, so oftentimes I'll just be like, fine, here.
Yes, sacrificial lamb.
But the number of times,
Self-sacrificing lamb.
the number of times, like, we would be sitting next to each other,
Right.
and we'd discuss the answer, and I'd be like, yeah, that sounds right. And I would have just said something, so I didn't want to say something again, because that gets a little weird, because it's just me talking. So I was like, you should answer this.
You can't
I
answer a
wouldn't.
question twice in a row.
I'd prefer not to, at the very least.
I would like to leave that behind in high school.
Yeah.
You'd think more people would contribute here.
Yeah, you really would. Especially because, and getting back to math a little bit, the amount of dinner table conversations, not only with us, not only when you two are here, but just generally that end up being math.
Yep.
Also, the amount of dinner table conversations overheard
Yep.
that end up being math, we were
It's
like,
so good. I love it.
It's so funny.
This environment simply did not exist in high school, for me at least.
No.
Like Vermont public school, I'd always I'd lament to my parents. I'd be like, no, I wish there were more people who are interested in it. Because
Right.
I ran the math club in high school. I was one of 2 kids who did competition math, and I was trying to promote it. I'd have donuts at math club meetings, and I would try and get more people to show up. But people simply were not interested in it in my school. Yeah, this is slightly tangentially related to this, just on the lack of interest in math on the whole though. A lot of people read for fun, And this was like generally not something that I really did a lot of in high school and middle school. But people would be like, you do math for fun, Ellery? Like, what? That's so weird. Like, imagine any time you're reading a book for fun, I'm doing a math problem for fun. And it would kind of like, I don't know if it would like click for people or like, I don't know. Like,
it's not clicking for him.
It's definitely not clicking for Liam. It's like, yeah, anytime you're reading a book, I'm doing a math problem.
I'm still a little disconcerted, to be honest. Like, I like solving math problems, I'll say that. And I think there is something fun about, getting to the solution or thinking it through. But at the same time, I think it's much more fun to, like, discuss a problem with someone and come to an answer rather than just, like, return to my room, search up a problem online, and just go, like, aha.
See, this is what I would do.
I think I have the middle point that'll make you get it. Cracking the cryptic. That's essentially, a Sudoku is essentially a sort of rearranged type of math problem.
All right, yeah, no, solving puzzles for fun.
Yeah, solving puzzles for fun. Like these math problems, a lot of the time, are just kind of like puzzles to me. There was this one competition in particular that I really liked, and it was called VSMC Talent Search, Vermont State Mathematics Coalition Talent Search, maybe. But the format of it was, there's 4 tests throughout the year, spaced like roughly equally throughout the school year, and you have a month to solve each one, and there's 6 problems on it. Right. And you solve it on your own, and you submit the solutions, and it's really just like honesty policy. Like, you're not really supposed to. You can like go through like your notes and stuff, but you're not supposed to be like looking up like, oh, how do you solve like similar problems? And the problems are all like creative enough that like you can't just like look up the problem. It doesn't exist online. So like cheating a lot of the time just like won't help you. But yeah, so it's 6 problems throughout the year, and they are brutally hard.
Nice.
And you just spend so long thinking about them, and like these, I loved them so much.
I'll be honest, that does sound like a lot of fun, but at the same time, I do prefer the type of things where you can collaborate with people.
Yeah.
Just because, a lot of the time, I mean, go to programming, right? Like the whole idea of talking to a rubber duck just because you need to think out loud and explain your solution. A lot of the time, I'm just looking at a math problem and approaching it from completely the wrong direction.
Yeah.
So if someone else walks up and suggests something, it's like, oh, you might be onto something here.
Yeah.
Like,
go ahead.
Do you remember that time? I mean, I wasn't even there, but apparently you and Tosha were working on a problem, I think for 18600. And you guys were just like working through some complicated algebra or something, and Timber just suggests something and it falls out immediately.
Yes.
That might just be a Timber thing, though.
This was fun. It was an interesting problem. It was some like constraint problem, and there's a way to solve it using AMGM. There's also a way to solve it where you just like take this function and take its derivative and like find the point where it's like at its maximum or something. You're trying to maximize something, and she just like considers this function, takes its derivative, and like solves it in like 30 seconds.
Yeah.
To be fair, I think Tosha and I were thinking about it from like the math competition perspective, which is like a lot of the time, like actually 100% of the time in these math competitions, you never need calculus.
No calculus.
Granted, if you use calculus in your solution, that's perfectly acceptable, and you're allowed to use it, but you never need to.
But they're designed so that you don't need calculus.
Exactly. So that's kind of the perspective that we were coming at the problem from.
That does actually remind me of another time, though. Remember when we were on the roof of Kresge?
Should we be saying this on a podcast?
I don't know.
Kresge is an affectionate term for the Simmons Terrace, perhaps.
We were chilling somewhere.
we were chilling somewhere, and we decided out of all things to be considering, actually, to look at the view that was available, right? And actually, we were considering the view from the Simmons Terrace.
Yeah.
And we were wondering, where on the terrace could you stand that you can see the most of the night sky, right? If you're modeling, your view as being in a circle, right?
Right. And the terrace obviously has like walls on either side. And, like if we imagine it's like a perfect square,
right?
I think we were simplifying it to be a perfect square. And on either side, there's like an infinite wall that goes up. Where do you stand on the terrace to get the most horizontal angle in front of you and behind you? If you were to like spin in a circle around you, where would you be able to see the most?
Because if you think about it, if you're standing bang in the middle of the square, right, then you have 180 degree of total view, right? Because you have 90 degrees, that's just one wall. 90 degrees, that's the other wall on the opposite side, and 90 degrees of complete space. Right? If you're standing smack bang on, like, I don't know, one of the corners.
Yeah, what did we, if we said we're on the corner, did we say that was a 180-degree view, or did we say...
So exactly on the corner, you had... I actually don't know how we modeled this.
I forget how we modeled it. That's kind of a weird edge case.
Where... Yeah, the edges are an edge case.
I think we said that was 225 degrees total. If you're at the corner.
I agree.
Like 180...
I think we said 180 this way, and then... Bang,
the 45 degrees 45 on the other side.
Yeah.
Are we looking... we're not looking up.
No.
No. You're only considering horizontal, like... Yeah.
Plus, you know, in general, we didn't want to get into the messy trig of, like, you know, if you're on one side, you can see over the wall a little bit more, but the view's not even good if you look, like, there's not that much difference, right? It's still just, like, certain amount of sky.
Does it depend on what's on this... Well, in real life, it does depend on what's on the skyline.
I think we were just considering, like, one plane of sight. Like, if, like, you take your eyeballs and, like, cast rays from them.
Like Minecraft.
Yes, exactly. And just, like, go like this and spin 360 degrees. Like, how much angle would you see that is not wall?
Yeah.
I think it's, like, the problem.
What were the findings?
I cannot remember.
I can't remember optimal solution. Was it on the corner, or is it dead center of...
The edge.
Dead center of, like, a terrace. Like, a non-wall edge.
Oh, no.
This is going to be embarrassing that we're... I don't know if we should be deriving this right now.
You know what?
There is limited time.
You keep talking. I'm going to be deriving this because this is going to be bugging me.
Okay, go ahead.
Yeah,
what else do we have? While Liam's doing that.
While Liam is rederiving this in
yeah,
his
we
head,
can have our own little chat.
Yeah, it's funny how much, you know, math-related stuff that you overhear, but it's interesting how hard it is for so many people to get into it.
This is something that I wanted to talk about when you said, like, I have this idea for a math podcast.
I did.
Yeah.
He's got it.
Same angle.
Wait,
middle. Yeah, it is the middle.
It is
of
middle?
Yeah.
Middle
And
of the
the reason, so it is the middle, not middle of the balcony, middle of the edge of one of the non-wall edges.
Say that again.
It is the direct middle of one of the non-wall edges of the balcony.
Okay. So...
So, you know, if you're in smack bang in the middle of the balcony and you see, you know, there are two wall edges directly opposite.
Yeah, that's what I meant.
Yeah.
I would have said middle of the terrace.
Right,
yes.
Yeah. And the reason for that, right, is because the angle you get at the corner of, so no matter where you are on the edge, you get 180 degrees of whatever edge you're on, right? If you're on the corner, you get 45 degrees of the opposite edge. Right? And that, you know, you can
just... We're going to end up with, like, arctan of...
No, not doing that. I mean, that's what you would have, but I can't do trig in my head because I don't think anyone can. If you're on the corner, right, you get 45 degrees of the opposite edge, right? Now...
Are you considering the rate of change of the view?
No.
Okay.
What I'm considering, and this is the argument that I made when we were talking about this last time that took forever to get across to you two, but... If you have a circle, right, one of the ways you can define a circle is that the angle that you get from a circle's circumference, right, is twice the angle at center. Which is to say, the angle from a circle's circumference is the same no matter where on the circumference you are, right? That's tended by 2 points on the rest of the circle. So, if you were to consider a circle that goes through the four corners of that square,
right,
no matter where on the circle you are, right, and two of the corners of that square are on the opposite side, the angle made by those two corners on the opposite side and the point that you're standing on the circle, so long as it's not in between those 2 points on the opposite side, so long as it's on that major arc, is going to be the same.
Right.
So that means the point that has a 45-degree angle is going to be on that circle, right? And the circle's outside the square. The square is inside the circle. So that point that's 45 degrees is going to be further away than the edge of the balcony.
Right.
Which means if you move back onto the edge of the balcony, that angle has to be a little bit wider than 45 degrees.
Oh, I can see it, yeah.
Right, and the closer you get to the center, like the closer you kind of are to that opposite side of the circle, those opposite 2 points of the circle.
For you to stay at 45-degree angle, the balcony would have had to use a theater term, a proscenium.
Yes, I have not heard that term, but I think you're right.
Yes.
Yes, we're going to hope that I'm right, and if not, we'll put it in. We'll put it in the captions. But to keep the same 45 angle from the corner, you'd have to go out further.
Yes.
Since you're not doing that, the angle must widen.
Right, the closer you get to like this like median of these 2 points, the wider your angle's going to be. Yeah.
Interesting. See, but why don't people get into this and do this? That's the question I pose you.
Yeah, so this is like I kind of have like a gripe with like the way that math is taught a lot in like elementary and middle school, and like as you're learning it, like for me the case, like I feel like it was very lucky that I was able to get into this. I had some like great math teachers early on who like introduced me to like competition math and like thinking about this like problem solving aspect from like this perspective. My dad did this with me a lot. I think for a lot of kids, you end up with situations where it's like learn these formulas and you don't have any intuition for where the formulas come from. It's just you're expected to be like a machine. You're given these numbers and you're given this formula and plug them in and here's the result you get and put it down on a piece of paper.
Yeah, absolutely.
There's no application of it. It's just like strictly here's the numbers, here's the formula, here's the output.
I mean, one of the most common like cliches in regard to math is when am I ever going to use this, right?
Yeah, there's no like creativity, a lot of people say. I think math is so creative.
Math is all creativity. It's all patterns and elegance.
Yeah. I mean, hey, don't have to convince me.
Yeah, preaching to the choir. But
convince everyone else.
Yes, indeed. That's the goal. It's so hard to, like, explain. I think it's hard if you don't have a visual or physical sense of things outside of the numbers on the page. And, like, for me, what gives life to math and what gives life to, like, an equation sheet is to be able to see the patterns and how they interact. And I grew up, I went to a Montessori school, and so that really helped me be able to, like, visualize things. So we had the Binomial Cube. Do you know this? So what it is, it's a little toy. It's very simple. It's essentially it's a cube that shows you what a plus b squared looks like. So you have on one face of this.
Oh, a, b.
Yes.
A, B, and then this is the A squared, this is the A, B, that's the B squared.
Yes.
And then you do that for a cube, and then A plus B plus C.
Oh, okay.
Yes.
Or A plus B cubed, rather, and then,
yes. And
so cool.
my teacher showed me that in 3rd grade. I wouldn't learn about algebra for a while, but she showed me that in 3rd grade, and and then she showed me it written out. A plus b squared equals a squared plus 2ab plus b squared. And from then on, I feel like a lot of my love for math is literally in the simplest algebra, because from then on it just made so much more sense to me to like see how the numbers sort of interact and like move with each other. Yeah, which is beautiful, and people don't get shown that, and so then they don't see it.
Yeah,
which is sad.
That being said, I do also like I really like that like visual math, and when you have these like interpretations of things,
draw a picture.
Yes, like drawing pictures and lovely stuff like that. But I also have like a very deep appreciation for like very like theoretical math and just like I don't know a lot of like number theory kind of boils down to that, where there's not like really like a nice way to like think about these like Diophantine equations a lot of the time, you know? Like,
Yeah. No, I
some
fall in love
Diophantine
with the
equations
numbers
you can.
first because
Yes,
you can see them,
sure,
and then.
sure.
For me, it's been like that's the way I got into it. But now I'm not a very visual thinker. But now I just see the numbers, and I can sort of internalize and intuit how they interact with each other and move in my head, like on an equation sheet. But yeah.
You know, I will say though, like I do like being able to visualize at least to some extent, or to intuit or to look at it in another perspective, and like. For me, at least, that's one of the reasons why higher dimensional calculus has always been so annoying to me. Because, like, okay, taking the gradient of a function, I can see that, going to 2 dimensions, all right, oh, no. Anything 3 dimensions or higher, it's just like, I don't want to draw this. What's a 4-dimensional gradient doing here?
Right.
Which direction are you even going? This is upsetting me.
When you get above like triple because triple integrals, you can think like this is like literally just like calculating like mass of something. If you have some some like surface and with like a changing mass density that you know, then a triple integral makes perfect sense.
Yeah.
But like anything beyond that is like there's not really a situation where I can see where I can like intuit that.
Yeah.
Same way like
maybe if you say the 4th integral is something like in physics if you're integrating. Oh no! What idea did you have?
Continue.
I mean, if you're integrating like the total amount of energy in something, and you're looking at temperature and density, and like looking at all these different variables, or if you add like time as your fourth thing.
I was
But
going to say temperature, was the only thing that made the fifth dimension make sense to me. It's like area plus time plus temperature at that time.
Gotcha.
yeah,
I was going to say in the physics example, like going into the realm of physics, the same way it's like hard for us to intuit like what like a fourth integral looks like. With physics, for position, you have like the derivatives of position, velocity, acceleration is still fine. I was able to come up with a way to kind of like feel what like jerk is, the derivative of acceleration, but like derivative of jerk, like I don't have a way.
Is that jounce?
I think it's jounce, crackle, pop, or snap, crackle, pop. I think it's snap.
Are you sure jounce and snap aren't separate ones?
I could be wrong. I thought they were the
sorry,
same.
Did you say snap, crackle, pop?
Yep.
Yes.
As in the
Our-
cereal?
Yeah.
No.
Like,
As- well, I mean, yes, I guess,
That's
but as
probably
in
where it
the
comes
time
from.
derivatives of acceleration,
Time derivative
of
So wait,
displacement.
wait,
of
I guess,
displacement, but like
originally.
those are yeah.
Which, like, fifth, sixth, like what?
Displacement, velocity, acceleration, jerk. Possibly jounce is a separate thing. Possibly jounce and snap as the same thing, and then snap, crackle, pop,
So what, 6, 7, 8?
I think
or
it's-
5, 6, 7.
But,
Yeah.
But we
it all
don't
comes-
know
Wait.
which one.
But it all comes back to 6.
4?
Yes.
Wait. No, 4 is jerk.
Yeah.
4 is def-
well,
no,
oh no,
3
no.
is jerk.
2 is acceleration. 3 is jerk.
3 is
4
jerk.
is jounce. So it's either 5, 6, 7 or 4, 5, 6.
Yes, agreed.
But you know what the
Anyway.
even worse thing is?
The
You can have time integrals
Yes,
of,
abscission and ab.
Oh, I thought it was absement.
Oh no, you're right.
Yeah.
It's absement.
Yeah, so displacement, the integral of that, the time integral of that is absement.
Okay.
There are very few situations that you use this that make sense to me. I'll be honest.
Wait. Oh yeah.
Like, I think there's
I mean,
one
like-
example in music, and like,
Well, absement makes sense because like absement
Okay.
you think of as like the total distance you've traveled. Because no.
No. So absement
know.
is like, all right, let's say you have a lever, right? A lever.
Right.
And, it operates as a switch. So let's say you have this tank filled with water, and depending on where the lever is, it lets out a certain amount of water, right? So if it's all the way up, it lets out, let's say, a liter per second. If it's halfway up, it lets out half a liter per second. If it's all the way down, it lets out, it puts in a liter per second. Halfway down, half a liter per second. And if it's directly in the middle, it puts out 0. So, if you want to figure out how much water overall is being let out of the tank,
Oh yeah, no, you're right.
you need to take the time integral of the displacement of that lever to see, and because the displacement of the lever corresponds to the liters per second being let out of the tank.
Right.
So you'd want the absement of the lever. And there are some instruments, apparently, that work like that.
Oh, interesting.
But they terrify me and they make no sense. But you know what's even worse?
Higher time integrals.
Keeps going.
See,
Absity, abceleration, abcirc, absounce, absap, absackle, I don't know.
Absop.
but math is really elegant, right?
Yeah!
Yes.
It's physics that causes the problems.
Yeah, physics is the only problem. But physics is math but less elegant. Chemistry is small physics. Biology is not my problem.
Have you seen the XKCD, which is like, psychology is just applied biology.
Yes.
Biology is just applied chemistry. And
Oh,
a
chemistry is
physicist.
just applied physics. Yeah.
And then a mathematician
Math way
over there. Hey, how's it going, guys?
Yeah.
This is all just applied math.
Yeah.
Of course, some might argue that math is just applied philosophy.
Ooh.
Oh, this is another like the logic branch of math is really and like
Right.
Yodel's incompleteness theorems. Like,
Wait, is it pronounced yodel?
is it not?
I always said Gödel.
Jodel. It's probably some sort of like
Euler or Euler?
Euler.
Euler.
My world is locked.
It's probably something between like a G and a Y.
Yeah, probably.
Yodel's. I don't know. Doesn't really matter.
But anyway.
Anyway,
You want to explain the theorem?
his incompleteness theorems. There's 2 of them.
Capital H for the his. We'll treat him that way. Continue.
There's 2 of them, and I'm probably going to butcher these to some degree. One of them is along the lines of any consistent system cannot prove its own consistency. So if we consider mathematics has this like set of axioms that we define that we kind of base all of math off of. Everything can be derived from these axioms.
I've heard of this.
So if we have any system, a system is considered consistent if it doesn't have any contradictions in it. But it's proven that if you have a consistent system, using its axioms that define it, you cannot prove its own consistency. So we suspect that our axioms are consistent, but it could be that one day contradiction pops up, and we would never see it coming because we can't prove it.
Right. So taking that to philosophy, if we're saying that math is just applied philosophy, couldn't you then extrapolate that it is mathematically necessary that we must have faith?
Oh, I kind of like that argument. I mean, because paradoxes do pop up in math from time to time. One we actually looked at in 18600, the Banaktarsky Paradox.
Right.
Basically says, if you treat a sphere as a collection of infinitely many points...
Uncountably infinite.
Uncountably infinite.
That has to be specified.
Yeah. You can separate these points and then put them back together again as two identical spheres to the original
same mass,
sphere.
Same density.
Is this the orange that's as big as the sun thing?
Yes.
I think
yes, this is like the Feynman's, yes.
Yeah.
We love Feynman here.
Yeah.
Yes, the same principle can be applied to that. Uncountably infinite points,
And anyway, the idea is that there are these two axioms that are generally used for most other things. The axiom of choice in probability, and what's the other one?
I forget what the other one.
Countable
additivity.
Yeah.
Countable additivity.
And if you put them together, they cause problems.
Right.
So you're just kind of like, we'll ignore that for now.
They can't coexist.
Yeah. But I don't know the solution.
Yes, but apparently it can be applied. The other application we were talking about is you take an orange peel and you break it up into uncountably or immeasurably tiny little pieces. You cut it. You put it back together and it's as big as the sun.
Yeah.
Right. Yeah.
The good news for that, though, is quantum physics says you can't do that, so ha-ha.
I think that's almost exactly what
Feynman says. You can't cut smaller than an atom, so therefore...
Well, you can.
Well, yeah,
You shouldn't.
You shouldn't.
Hey, I'm a nuclear scientist. I'm all about cutting smaller than atoms.
Let's not today.
It's time for another
episode.
Although,
I do very much like that idea that because of the incompleteness theorem, you could make an argument that maybe it's mathematically necessary to have faith.
Yes.
I like that.
What's the other incompleteness theorem? So there's... Okay, fair enough. Yeah,
You're asking the wrong guy. Look, I basically just intuit the incompleteness theorems. It's like, there are problems.
Wait, you guys talk for a second. I want to try and see if I can come up with the other one.
While he tries to reinvent this theorem...
See, this is the problem about talking about math, though.
Yeah.
Anytime we get to something that we know we should know or know we can know, each of us will do our... it's going to bug us.
Right.
If I did not solve that balcony problem, I would have been thinking about it for the next...
Until you solved it.
Yeah, pretty much. At least a while.
I want to give an example that I've read about that actually... what I will do is I like reading books about mathematicians, and I've read... there's an excellent book about... It was like Fermat's last theorem. There's an excellent book about it, and essentially the story is there's a very simple problem in math. It's essentially like you think of x squared plus y squared equals z squared. Immediately the example is 3, 4, 5, right? Now, x to the n, let's say it's 3, for example, plus y to the n equals z to the n. Let's say n is 3. That doesn't work. It's very hard to come up with.
There are no
X, Y, Z are
integers.
integers.
There's no integers that solve it.
Distinct.
How about 4?
Yes.
No. How about 5? No. And that's a very simple problem that Fermat, who is a 1800s maybe French mathematician
I want to say like late 1600s.
Who liked trolling people in his margins. He wrote it down and he was like, I have a very clever proof of this that will not fit in the margins. And then 200 years later, this guy, Andrew Wiles, who hadn't been able to put it down since he was 11, he read it in a little math problem book and he was like, I'm going to solve this. He had to bridge two fields of mathematics that were both not invented at the time of Fermat to solve, using, I think, a 300-page proof, this simple question.
Yep.
Yeah. I'm not going to come up with the other
theorem.
Incompleteness theorem. It's not coming to mind.
No,
Consistency.
It's crazy. And I think there's still a lot of historical debate over, was Fermat just trolling us?
No, he definitely was. I bet he tested a bunch of cases and had some sort of intuition for like I feel like it's not true. That's my bet.
I don't know, because there is a reason for like stuff being written in the margins, stuff being written in places. Paper was in really short supply.
You're telling me that like 350 years later, something that like this man did that nobody was able to come up with.
Well, I mean, you know, one of the things is it really depends how you approach a problem. Maybe he just saw something that nobody else thought of. I mean, think, you know, this is moving again to physics, but think about like De Broglie got a Nobel Prize for a 1.5-page PhD thesis, which was just like everyone had been talking about, you know, how particles have wave-like properties. And then De Broglie was just like, what if waves have particle-like properties as well? And then he just wrote like a page and a half, and it won him the Nobel Prize. And it's just like, oh, did nobody thought of that?
Well, it's the same way that like, I mean, I guess like nowadays, like, you know, calculus was like figured out in like what, early 1700s, late 1600s.
I never know the dates.
I don't know dates either. Actually, I'm really bad at that. But you know, now this is something that we just learn like really easily. Same way in 18600 we derived black shoals, which is something that MIT professors got a Nobel Prize for, and we're doing this on a problem set now.
Yeah.
And it's just something where it's like a lot of the, I mean, black shoals is not an example. But not a good example of this necessarily. But a lot of the times it's like these...
Also because we skipped that problem set where we had to derive it, or at least that question.
Fair enough. Yes, but these ideas where it's like it's not like super hard to grasp, but coming up with it on your own is incredibly difficult. And that's why a lot of these competition math problems are that case where it's like you read the solution, it's like, oh, I can do that. I know how to do that. But actually coming up with it on your own is brutal.
I still think geometry is the worst at that. Like, proof by just constructing this magic line that now allows you to angle chase everything, and it's easy. And it's just like...
Yeah.
Who would think of it?
But maybe some of those problems are going to be the ones that inspire kids to then be the ones to solve or the new problems that the new kids will have to be able to solve. And that's a full circle moment with a triangle inscribed in it. And on that note, and on that terrible, terrible joke,
so I guess that's...
we're going to end it here. Thank you so much for listening, and this has been On the Dome. Full circle moment triangle.
No!
Now let's talk about the mathematical properties of domes.
This is the song that I wrote. I did like one like actual composition ever, Stuck in the Corner of a Circle.
Yes.
No.
I wrote this song, Stuck in the Corner of a Circle.
No.
Yeah.